Welcome back to Math 151. At the end of the last video, I asked you to consider these 4 derivatives and think about which of them you would compute using logarithmic differentiation. And in the last video, we discussed the following criteria. We want that the top level operation, when we're computing our function, is not plus or minus, because we don't have log rules for those. So let's look through these one at a time and see what's going on. In A, we're taking tangent x and raising it to the power x minus 7. So the two pieces that we're assembling are tan x and x minus 7. And the top level operation is exponentiation. That was one of the good operations because there's a log rule specifically about exponentiation. Not only is this something where you can use logarithmic differentiation, but in this case, you must. There's no other derivative rule that will work. In B, we have the same two pieces, x minus 7 and tan x, and we're assembling them at the top level as a product. So we can use logarithmic differentiation, but we don't have to. You could equally well use the product rule. C has top level operation minus, which is bad. Here our pieces are not x minus 7 and tan x, but x and 7 tan x. There's no log rule for that top level operation of minus, so we should not use logarithmic differentiation. Otherwise, in step 1, we won't be able to simplify ln fx at all. And it will turn out just as silly as the non-example we had in the last video. What about D? Well, here to D, we're back to our two familiar pieces, tan x and x minus 7, and they are being put together with division, which is good. We have a log rule for division, so we can use logarithmic differentiation. Here was our first example, A. A problem could just say, compute this derivative. And here's what you would do. You would first, in step 0, decide to yourself, I want to use logarithmic differentiation, because what I have here has a changing base and a changing exponent, so I have no choice. I have to use logarithmic differentiation. And then you might just write down, let f of x be this thing you want to take the derivative of. Or you might even write down the words logarithmic differentiation. But what I've written here is fine. In step 1, we're going to compute ln fx. And we know from our log rules that that exponent x minus 7 comes down. And the whole thing, that whole exponent x minus 7, multiplies ln of the base, which is tan x. It's really important to have these two parentheses around x minus 7. And notice that I do write down on the left side ln fx. That left-hand side is always going to be the same, but it's really to your benefit to write it down. It'll help you remember where you are in the procedure and what you're doing. And it will also help the person who's grading your work to see that you know what you're doing. Even if you make a computation error, they'll be able to tell that you're carrying out the correct steps. And now it's time to move on to step 2, which is when we differentiate. So on the left side, when we differentiate ln fx, we always get f prime x over fx. And now on the right-hand side, we have a product, so we have to use the product rule. The product rule says first we'll differentiate x minus 7, which gives us 1, and leave the other thing alone, leave natural log tan x alone. And then we add to that a term where we leave x minus 7 alone, and we differentiate ln tan x. So when we differentiate ln tan x, we have to use the chain rule. Tan x goes in the bottom, and in the numerator goes the derivative of tan x. Think for a second, do you know what the derivative of tan x is? It's secant squared x. Good, now we're ready for step 3. Which is to multiply by fx. So we have f prime, and then that equals whatever we had, no need to simplify it, times f of x, times the original thing, which in this case is tan x raised to the x minus 7. So that would be the end. And you might even want to box your answer there. Here's our next example. Computing the derivative of the product, x minus 7 multiplied by tan x. Here in step 0, where we're deciding what to do, we could decide to use the product rule, or we could decide to use logarithmic differentiation. Since I'm trying to demonstrate that method, I'm going to go ahead and use logarithmic differentiation. And we start again by saying, let f of x be the thing we want to differentiate. And then in step 1, as always, we're going to compute ln of fx, simplifying it as much as possible. Here we have a product, which log rules tell us turns into a sum, ln of the first term plus ln of the second term. Now in step 2, when we differentiate, we always get the same thing on the left. And now each term we just differentiate, taking care to use the chain rule. So for ln x minus 7, we get the thing inside and the bottom. That's how you differentiate ln. And then on top you get the derivative of the inside thing, which here is just 1. In the other term, you get tangent x in the bottom and secant squared x in the top, just like we did in example A. And then step 3 is just multiplying. Now, as I've said before, this is a perfectly good answer. You don't need to simplify any more than that. But I am going to, just to illustrate a point to you. If we multiply this out, in the first term, the x minus 7's cancel, and you get 1 times tangent x. In the second term, the tangents cancel, and you get x minus 7 times secant squared x. Notice that this is exactly the same thing that you would have gotten by using the product rule. Here's our third and final example. C was a non-example, so we're not going to spend any more time with that. Again, we don't have to use logarithmic differentiation. We only had to for part A. So here, if step 0, if we decide to, then we start the same way we always start. Let f be the thing we want to differentiate. And then in step 1, we take the log. Now the log rule for quotients says a quotient on the inside of the log becomes a minus outside. So you get ln of the numerator minus ln of the denominator. And then you can't simplify any further. So we go on to step 2, which is differentiating. Looks very similar to what we had in the last example. ln of tan x, we already know that's secant squared x divided by tangent x. And ln x minus 7, we already know the derivative of that is 1 over x minus 7. But in step 3, when we multiply, it comes out a little different than it did for the product. Because here, there's still a tangent in the bottom of the first term and a tangent in the numerator of f, so those can still cancel out. But there's also an x minus 7 in the denominator of the second term, and an x minus 7 in the denominator of f of x. So when you multiply this all out, then the new denominator would be x minus 7 squared. In the first term, we would get secant squared over x minus 7, and to make a common denominator, that's going to become secant squared x times x minus 7, and then minus. And the second term has tan x over x minus 7. I'm going to write that as 1 times tan x over x minus 7 squared. Because now you can see this is exactly what the quotient rule would have given you had you applied the quotient rule instead. So just like in the last example, that's not work that you need to do to answer this question. It's just to illustrate the point that you get the same thing doing this on a simple quotient as you would if you just used the quotient rule. When we look for our criteria in step 0, why do we say that we're looking for products, quotients, and exponents? Why don't we just say exponents if that's the only time you need to use this? Well, the reason is that you can have examples which are really complicated, which have products, quotients, and exponents. For instance, remember back when we computed this derivative of sine x raised to the 7th times e to the x over x squared plus 1. we don't have one of those exponents with a changing base and a changing exponent. We just have products and quotients and regular exponentiation, where here with sine x raised to the 7, the exponent is just a number. So we could very well use all the tools we already have to compute this derivative. But it's much easier with logarithmic differentiation. So, as we said, our criteria is that we can use logarithmic differentiation as long as the top level operation is not plus or minus. We must use it if we have an f of x raised to the gx thing. That is, if we have an exponential thing where the base, written here as f of x, is changing, and the exponent, written here of g of x, is changing, then we must use logarithmic differentiation to compute the derivative. And there's one more category, which is that we don't have to, but we probably want to, if there's a complicated product or quotient, like what we see above. So that's how you decide when you want to use logarithmic differentiation. Let's focus a little bit on that must. Here are 3 examples where you must use logarithmic differentiation. All of these have something where the base depends on x and the exponent depends on x. Base, exponent, base, exponent. Try to use logarithmic differentiation to compute each of these derivatives before you move on to the next and final video.